Swayam Prabha. Digital India. Educated India.
So, in today's class, we will start our discussion on particle response time, which is a very important concept in dispersed multiphase flows. Now, what is meant by response time? So, let's say you are crossing a road and you saw that a vehicle is approaching, so you suddenly stopped. So, you responded to the situation. Faster the vehicle speed, smaller should be your response time if you want to be on safe side. Okay. So, similarly, now if we consider, let's say you have a flow in which you release one particle. So, initially the particle velocity is 0. Okay. So, now how long it takes for the particle to adjust with the flow, which means that how long it takes the particle to reach the velocity of the flow. Put it other way, let's say you inject the particle at some initial velocity, which is, let's say, higher than that of the flow velocity. Okay. Then how long it takes the particle to reach again the velocity of the flow? That is, in that case, the particle velocity will reduce. So, this is what is the is meant by the response time. And although in these examples we are talking about the momentum exchange between the two phases, we can also have a response time with respect to energy exchange. Let's say the temperature of the flow is given and you inject the particle at some initial temperature. So, how long it takes the particle to attain the temperature of the flow? So, we can define a response time based on the heat transfer also. Okay. So, first we will start with the definition of momentum response time. So, what is momentum response time? Now, for this one we need to consider the forces acting on a particle. Okay. So, again, if we go back to this example where we release one particle in the flow, then what are the forces acting on the particle? If we assume that there is no gravity, what forces act on the particle? Drag force. Okay. If we also assume that the particle density is high enough to so that we can neglect buoyancy effect. Okay. So, now how do we express the drag force on a particle, assuming that it is a spherical particle? Stokes law. But okay, so what is Stokes law? So, for that we have to consider basically the starting point is Newton's law. So, the mass times acceleration, that is the force on the particle, is equal to the drag force. What is the general expression for drag force? Okay. Now, this is coefficient of drag, this is carrier phase density, this is the projected area, and this is velocity of the particle. Okay. Now, but is this expression correct? The question is, there should be a negative sign, but why? Why do you think there should the drag should be associated with the drag force should be associated with a negative sign here? Now, look at this. Here we have particle velocity, okay, but there is no effect of fluid velocity here. So this should be the relative velocity between the phases. So when we derive Stokes' law, we consider it from the reference frame of the particle. That is why the fluid, this velocity is the fluid velocity. Initially I wrote fluid velocity, not the particle velocity, I am sorry. So, but this fluid velocity is the velocity with which the flow approaches the particle. In our case, this should be written as square of relative velocity. Okay. Now, but still, if you look at this term, okay, here this refers to a scalar quantity, right? But how about the force? Is force a scalar quantity? No, it's a vector quantity. So how do we account for that here? So how do we know the direction of the force? That's what is the question. Okay. So though this expression refers to the magnitude of the drag force, okay, to understand the direction we need to express it this way. Okay. So actually the expression is this. Okay. So you can understand it again by considering this simple example. So now let's say the fluid is at rest, okay, and you inject a particle with certain velocity. So the fluid is at rest and you inject the particle with some initial velocity v0. Okay, so now what will be the direction of the drag force? If this is the direction of motion, what will be the direction of the opposite? So in that case, this term will be 0 because the fluid is at rest. So this gives you that the direction of drag force is negative. But now consider the other case where you inject a particle into the fluid which is moving at certain velocity. So in this case, initial velocity of the particle is 0. We are releasing from 0 velocity. So this will be 0, and so the direction of the drag force is along the direction of the motion. So in this case, actually the fluid is dragging the particle along the flow, while in this case the fluid is resisting the particle motion. Okay, and this is accounted in through this expression. We can express the mass of the particle as density time the volume of the particle, and we can now invoke the Stokes drag law, according to which the coefficient of drag is given by 24 by Reynolds number, where Reynolds number is equal to density times diameter times the magnitude of the relative velocity divided by the viscosity of the carrier phase. Okay. However, we have to keep in mind that Stokes drag law is valid only for very low Reynolds number flows. Okay. So with this assumption, we can introduce this expression for the coefficient of drag in here in the expression for drag, and if we simplify it, we will get an expression like this, a simple expression like this. That is, on left side you have the acceleration, and on right side you have the relative velocity divided by this term, density of the particle times d square divided by 18 times the dynamic viscosity of the carrier phase. Now, what is the unit of this term in the denominator? Look at left side. This should be time. Now, So this is velocity by time. So this is time. Okay, and this is known as particle relaxation time or momentum response time. Okay, so the acceleration of the particle is equal to the relative velocity divided by the response time. This is called momentum response time, also particle response time, aerodynamic response time. Sometimes we also call it aerodynamic response time. Now we will see the significance of this. So now if we consider the specific case where the flow velocity is constant and this is equal to u naught, and initially the particle velocity is constant, is 0. Then if we solve this simple differential equation, then we will get this expression. Okay, so we can use the limits that the particle velocity is initially 0 to some velocity v, and the limits for time is from 0 to some time t. Okay, so then we see that there is a exponential term involved here. Okay, so if we put t is equal to tau d, that is the particle relaxation time, then we get that the particle velocity is equal to 0.63 times the flow velocity. So which means we can define the particle relaxation time as the time required to attain 63% of the carrier phase velocity. We can also write a general expression for this by considering some initial velocity here. Okay, so you see that the particle relaxation time or momentum response time basically depends on the particle density, then viscosity and diameter. Okay, but it is more sensitive to the diameter because there is a d square term involved in it. We can quickly check by considering an example of water droplet in air. Let's say you have a 100 micron droplet which is moving in air. Then this the particle time constant we can easily calculate using the expression that I had shown earlier, that is from this expression we can calculate the particle relaxation time, and this turns out to be 30 millisecond. Okay. Now what will be the particle relaxation time for a droplet of diameter, let us say 10 micron? It will be smaller than this. Okay, but how much smaller? So you know that the particle relaxation time is proportional to d square. So if you reduce the particle size by 10 times, then the relaxation time will reduce by 100 times. So that is why it is very sensitive to the particle size. So what does this mean? This means that if we introduce two particles, one 100 micron, one 10 micron into the flow, then this small particle will get adjusted to the flow very quickly, much more rapidly compared to the large particle, which is intuitively expected as well. But here we could quantify this relation, and that is what is important. Okay, so but if we just assume that the flow velocity is 1 meter per second, then we can calculate the Reynolds number here in both cases, and you see that in this case it is about 6 while this is 0.66. So our the derivation is actually valid for this case. Okay, while for this case we have some effect due to the finite Reynolds number which is larger than 1. So this can be accounted by considering a modified expression for the drag force. So then you can also try using this expression in the this expression to derive the moment to solve the momentum equation. But can you solve it analytically? Can you solve? So if you put this expression for coefficient of drag in the original equation for momentum, rate of change of momentum of the particle, can you solve this analytically? How we solved? So here if you see, we have solved this analytically. It's just separation of variables. But because of this nonlinear term, you can't solve it analytically. However, it is possible to solve it numerically. Okay. Okay. Next. Next, we will consider the thermal response time. So, thermal response time is the time required to respond to change in temperature of the carrier phase. So, we can do a similar analysis. Now, in this case, what is the governing equation? The governing equation is nothing but the application of the first law of thermodynamics. Okay, that is, the rate of change of internal energy of the particle is equal to heat transfer with the surrounding. That's all. So here this term CD here refers to the specific heat. Actually, I should write here CPD. Okay, that is to differentiate from the coefficient of drag. Okay, so this is the specific heat. So this is the rate of change of energy of the particle. No, time required to respond to the change in the carrier phase. So here still we are writing the equation for the particle only. Okay. So again, so you can think of this simple situation. So this is the temperature of the carrier phase, this is the temperature of the particle. Okay. So this equation is for the particle. The carrier phase temperature is constant, we don't have to solve for this. So then here you see we have the heat transfer coefficient and the surface area of the particle and the temperature difference between the particle and the carrier phase. And then again by doing a similar analysis, so by introducing the particle size into this equation and rearranging these terms as shown here, such that we can bring in Nusselt number, okay, into the equation. We can express the rate of change of particle temperature, okay, which is equal to Nusselt number times this term multiplied with Tc minus Td, that is the temperature difference between the carrier phase and the particle. Now again, if we assume Stokes flow, that is, you have very low Reynolds number, then this will be, the heat transfer will be dominated by which mode? If the Reynolds number is so low, if the Reynolds number is very low, okay, this will be conduction. So that is why Nusselt number will approach 2. So by introducing that, we can rearrange and write the expression this way. So now the rate of change of particle temperature is equal to Tc minus Td divided by this term, and interestingly this term has also the unit of time, and this is known as, I am sorry, this should be thermal response time. This is known as thermal response time. Okay. Now what is interesting is the similarity between these two equations. So, the momentum equation, we could show it in this form, and now from energy equation we get this expression. So, you see, we are considering here entirely two different phenomena, momentum transfer and energy transfer, but still the mathematical expressions which govern them are basically similar, very similar. So, now by following similar method, we can solve this equation, okay, and find and we can also show that the thermal response time is basically the time required to attain 63% of the initial temperature difference between the two phases. So, in that case, it was, so in case of the momentum response time, it was the time required to attain 63% of initial velocity difference between the two phases, and in this case it is the temperature difference. And here also we see we have similar dependence on the particle size. It is sensitive to the particle size. So, again, if we consider a water droplet in air and if we calculate the thermal response time, we see that this is about 145 millisecond, and for a 100 micron particle size, and if the particle size is 10 micron, it is 100 times lower. Okay. Now, if you consider the thermal response time and compare it with the momentum response time, which is larger, you remember what did we get for the momentum response time? It was about 30 millisecond. So, this means that in this case the momentum equilibrium will be established more quickly compared to thermal equilibrium. Okay. So, now we can compare these two response times, and we can, it is possible to show that. So, this is basically dependent on the ratio of the specific heat of the carrier phase to the dispersed phase and the Prandtl number. What is Prandtl number? Ratio of kinematic viscosity to thermal diffusivity, nu by alpha. So, for gases, Prandtl number is of the order of 1. So, the two response times are comparable. So, comparable means you can say that they are of similar order, not same, but similar order. Like in this example, in one case it is, in our case the momentum response time is 30 millisecond and thermal response time is 145 milliseconds. So, they are comparable. But for liquids, Prandtl number is much larger than 1. So, in that case, the momentum response time will be much smaller than the thermal response time. Now, we have defined the response times, but if you see what is the practical use of those numbers. So, if I tell you that for water droplet in air and 100 micron water droplet in air, the response time is 30 millisecond. So, is it very large? Is it very small? What do you think? We cannot conclude anything unless otherwise we compare it with some other time scale. Okay. So, what is our objective here? Our objective is to understand how fast the particles respond to the flow. So, that is why we need to compare the response time with the flow time scale, with the time scale of the flow. And accordingly, we define a very important non-dimensional number in dispersed multiphase flows known as Stokes number. So, Stokes number is the ratio of the momentum response time of the particle to the flow time scale. So, now what is meant by flow time scale? Flow time scale or characteristic time scale of the flow. So, let us say you have a channel in which air is flowing with some average velocity u0, and let us say the channel height is L. Then what is the time scale of the flow? So, this is the flow time scale. What does this mean? This means how long a fluid particle would take to cover a distance equal to characteristic length scale of the flow. So, that is known as the flow time scale or characteristic time scale of the flow. Okay. So, now why we want to compare with this, with the flow time scale? Now, what happens if the Stokes number is much less than 1? This means that the particle relaxation time is much less than the characteristic time scale of the flow. So, in that case, the particle would respond fast or small or slowly. So, you imagine by the time a fluid particle, okay, moves a distance equal to the characteristic length scale of the flow, the particle has already adjusted itself with the flow. So, the response is very good, okay, and that is why we call those particles as flow tracers, because they follow the fluid streamlines very closely, okay. They are not fluid particles, but they can follow the fluid very closely. So, that is why in visualization experiments in fluid mechanics, we use tracer particles, for example, smoke particles, or we use smoke generators, so that we introduce particles into the flow because we can visualize the flow better. But what is the assumption? The assumption is that they are faithfully following the flow. If they don't, they are not flow tracers. So, you might have heard of particle image velocimetry technique, PIV technique, for measurement of fluid velocity. We'll discuss that towards end of this course. So, in that case, we introduce the particles to the flow and we actually measure the velocity of the particles. But we have to make sure that the particle size is such that they are following the flow faithfully. So, you see, if we have Stokes number much less than 1, we can assume that the particles to follow the fluid perfectly. But what happens if the Stokes number is much larger than 1? Physically, how do you visualize this? The particle relaxation time is much longer than the time scale of the flow. This means that if you inject a particle into the flow, it does not respond to what the flow is doing. It is going on its own. Okay. So, they move basically ballistically without responding to the flow, or you can say with minimum response to the flow. Okay. Now, what happens if Stokes number is of the order of 1? Then a very interesting phenomena takes place, is known as preferential concentration effect. So, in this case, the particles follow certain scales in the flow. Now, this is very relevant to turbulent flows. So, when we discuss turbulent a particle laden turbulent flow or particle turbulence interaction, we will consider this is in much more detail. But for the time being, I just want to show you just want to give you a glance of the beauty of particle turbulence interaction. So you see in this case, so you imagine you have a flow in which you add particles such that the particle Stokes number is very small, 0.05. So you see that the particles are everywhere, they are distributed. They are randomly but homogeneously distributed. If the particle Stokes number is large, like 8 or so, then also you see that some kind of, they are uniformly distributed only. Okay. But once the Stokes number is of the order of 1, you see this kind of preferential segregation of the particles leading to so-called particle clustering. Okay. So this is a very interesting fluid dynamics phenomena in particle laden flows. Now, here I gave you a simple example of a channel flow, but there are flows in which the flow time scale itself varies as you move along the flow. That is also possible. So, for example, let us consider a jet. Jet means, you imagine you have a tube through which, let us say this is air, through which air is coming out, and the air expands as it moves away from the nozzle exit. Now you imagine you introduce a particle here. The question is how the particle will behave, whether it will be a flow tracer or a ballistic particle as it moves along the flow. So now in this case, question is how do we define the Stokes number? So how would this change along the particle motion, along the particle trajectory? How would the particle relaxation time change? Because it is dependent only on the size. So if there is no evaporation or condensation on the particle, let us say you introduce a glass particle. So particle size is not changing, particle density is not changing, dynamic viscosity of the fluid is not changing. So particle relaxation time won't change. Now how about the time scale of the flow? So right at the exit of the injector, okay, we can define the time scale as, again, so if the diameter, let us say here is d naught and the average velocity is u naught, then d naught by u naught is the time scale at the exit. But as the fluid moves in the axial direction, it expands. So what happens to the fluid flow time scale? What happens to fluid velocity? What do you think? Fluid velocity, what do you think? It should decrease. Okay. So, but what happens to the characteristic length of the flow? It increases because the jet is expanding. So what will happen to the flow time scale? So flow time scale is basically characteristic length scale of the flow, which is nothing but the diameter. So the characteristic length scale is increasing, okay, but the velocity is reducing. So the flow time scale will be larger, which means that flow will become slower. If the flow is slower, then the characteristic time scale is larger. Then what will happen to the Stokes number? It should, along this direction, what will happen to the Stokes number? It will keep on decreasing. So the point here is that the same particle which may be ballistic in nature at the exit, it may be a flow tracer away from the injector exit. So in the same flow, the behavior of the particle is changing. Okay. Now, why this plays a very important role in turbulent flows is that a turbulent flow is characterized by existence of a range of length scales and range of time scales of turbulent eddies. So now imagine you have one particle but so many time scales of the flow. So you have one particle which is interacting with eddies of different size. So the behavior of these particles to eddies with different size would be different. For one eddy it may be flow pressure, for other eddy it may be a ballistic particle. Okay. So now imagine you have particles of different size, small to large particles. So in one hand you have particle size varying widely, in the other hand you have length scale of or time scale of the turbulent eddies varying widely. So you can have so many Stokes number defined, and that is what makes particle turbulence interaction interesting, and this we will see this somewhat later. Okay, so now at this point of time it is very important to distinguish inertial regimes versus Brownian regimes in particle dynamics. Now imagine we go on reducing the particle size. What will happen to the Stokes number? Same flow, but you go on reducing particle size. So obviously the Stokes number will go on reducing significantly because it depends on d square. So we can expect the particles to follow the fluid more faithfully. But what happens when particle size is below about 0.5 micron? Brownian motion becomes significant, especially in slow or quiescent flow regions of the flow. What is meant by Brownian motion? So I am sure you must have experienced this in a dark room. If you shine a beam of light, you will see particles moving here and there. The question is, can we call them as dispersed particles? And if you have noticed clearly, the motion of those particles is always random. You won't see a particular particular velocity associated with the particle. They move randomly. Why is this so? That motion is basically governed by the molecular collisions. Collision with what? Collision with molecules of the gas phase. They are so small that the collision with gas phase can influence their motion, and that is what is Brownian motion. Okay, so that is why the temperature plays a role here, and in this case the phenomena can be described by considering kinetic theory of gases. Now the whole point here is that we have to distinguish between the inertial particles and such particles. In our case, our focus is only on the inertial particles. Okay. So we always deal with inertial regimes where Brownian motion is negligible. Why? Because the convective velocity is much larger than the random motion due to Brownian motion. Okay. So those dust particles in the room, see in that example, the fluid is at rest. There is no bulk velocity or convective velocity of the fluid, but still particles are moving. Why that is so? Because of the Brownian motion. So there is a velocity associated with those particles, but if the velocity, the Brownian velocity is much smaller than the convective velocity, then we are in the inertial region. And this relative importance can be characterized by a Packlet number, which is which you can express the Peclet number through this. You can think of this as the ratio of the convective velocity or flow velocity to the characteristic velocity due to Brownian motion, which is nothing but the ratio of the Brownian diffusion coefficient and the length of the and the characteristic length. Okay. So, if the Peclet number is much larger than 1, it is flow dominated. If Peclet number is much smaller than 1, it is dominated by the Brownian motion. And you see that this Brownian diffusion coefficient, okay, plays a very important role here, means in defining the Peclet number, and that is proportional to temperature and the particle size. So, if the temperature is high or particle size is small, then this diffusion coefficient, Brownian diffusion coefficient, is larger, and accordingly the Peclet number reduces. And if it is much less than 1, we have the motion dominated by the Brownian motion. Now, you can ask, why should we care? This velocity is much smaller than the bulk velocity that we encounter in natural or engineering application. But even if the flow velocity is high, even if you have supersonic flow, if you have any boundary present, then there is a presence of boundary layer, because the velocity on the boundary must be 0. So, close to the boundary, the flow velocity is much smaller. Okay. So, there, if the particle size is small, then the Brownian velocity may be comparable to the local velocity. It may not have any engineering significance, but this may be possible. Okay.